starting in the middle of the game here. Hi, Emily, and others listening to this recording. What we're doing this week is we're going to be tying together our antiderivatives to the definite integrals. There seems to be a notational connection, and so we wonder, why do we use the same notation for the one, which is the net signed area under the curve, and we use a very similar notation for the antiderivatives? Why is that? We're going to answer that question this week. And so to get there, we started with this problem. A particle is at x equals 2 and t equals 0, and it travels with the velocity of v of t equals 2t minus 4, where velocity is in meters per second and t in seconds. And so then the question was, where will the particle be at t equals 3 seconds? And so we had, when I asked this question, we had a number of different approaches in the class. A whole lot of people did this with an antiderivative. They found the position as a function of time t, and they found that that was equal to t squared minus 4t plus 2, and then they just plugged in 3 in order to find the position. Other people said that the position at 3 is going to be equal to the position at 0 plus the total change in position, which is the integral of the rate, or the integral of the velocity from 0 to 3. And when they did that, they found that that was equal to -1 as well. So two different ways, very conceptually different ways of solving the same problem. And so we had just gotten to the point where I was about to discuss what this looks like on a graph of velocity. My velocity is equal to 2t minus 4, and so here comes my velocity curve, a line with an intercept of -4 and a slope of 2. And so when I integrate from 0 to 3, the velocity, what I get is the area of two different triangles. And the area down here is going to be negative because the triangle is below the axis. And so I'm going to get, if this is -4 right here, I'm going to get 1/2 of base times height. And the base is 2 and the height is -4, so that I get a total area of -4 right there. And over here, this is the point 3, 2, so that I get 1/2 of base times height for a total area of 1 right there. And so when I integrate from 0 to 3, that's equal to the integral from 0 to 2, which is -4, plus the integral from 2 to 3, which is +1, to give me a total area of -3. And so I could evaluate this integral either using the calculator or straight off of the graph. Does everybody see the flexibility that we have in terms of evaluating the integrals? Okay. Now let's ask a more interesting question. And that question is going to be, what is the leftmost, that is the minimum position of the particle? What is the leftmost or minimum position of the particle? Now there's no domain given, so what domain is implied? What's the smallest time that I could possibly have? 0 probably. And what's the largest? Infinite. Right. So our domain is implied here for t's greater than or equal to 0. And what strategy do we have for finding minimums all the time, every time? Could be endpoint analysis. I need a critical point. Right. The first step is to find a critical point, and then after that I have a choice between critical and endpoint, or what's my other option? Sine of f prime. That's right. And I'm not sure yet which one I'm going to want. Although there's a strong clue in the fact that I have an endpoint out here. Okay. So I need a derivative. I need a critical point. But I need a derivative of what quantity? Position, because that's what the problem is talking about. So I need the derivative x prime of t. this assumes that I have a function for x of t. If you took the first approach with the antiderivative, then you actually already have an x of t, and you can differentiate it. What is that x of t? It's v of t. That's exactly right. The derivative of x of t is just the velocity, which is equal to 2t minus 4. And that immediately gives us a single critical point, which is going to occur when t is equal to 2. And because I have a single critical point, it strikes me that sine of velocity or sine of x prime analysis is probably my winner, especially because I don't have an endpoint out at infinity. So I take a look at the velocity at t equals 2, and I'm going to label this either as x prime or as v. June, here's my labeling again. I'm labeling this as one or the other of those. And now I look at the sign, and you can read the sign straight off the graph. What is the sign of velocity for t is less than 2? It's negative. And for t is greater than 2? Positive. And so I can immediately argue that x of 2 will be the minimum because x prime is negative for t's less than 2 and positive for t's greater than 2. And we've seen this language before. This is exactly the language that we need to justify a minimum value. Well, that almost answers the question. It doesn't tell me the exact value of x of 2. So how do I find x of 2? I've got some options. Since I have a formula for x, I can plug in directly here. And I find that x of 2 is equal to 2 squared minus 4 times 2 plus 2, which turns out to be equal to 0. No. Negative 2. There we go. Or I could just as easily write that x of 2 is equal to x of 0 plus the integral of the velocity from 0 to 2. See how I'm using a definite integral to construct the same quantity here. And so that gives me the initial position 2 plus the value of the integral, which I already wrote in here in my diagram. That integral was negative 4, and that gives me negative 2 as a position also. So the first lesson to be learned from this is that I can answer the same kinds of questions with antiderivatives that I can with definite integrals. That tells me they're really computing the same thing. Yes?
If you find the rightmost in this
The
equation,
rightmost position will be infinite because the position keeps on increasing. And so it goes out to infinity. Good. Any other questions? Now I want to come back to an idea. We needed a critical point. That was the first part of our analysis. And once we had the critical point, then we did the sine of f prime analysis like that. And that was all fine. But what would I have done to find a critical point if my approach was to use a definite integral? How would I construct the position as a function of time t if I was using a definite integral to do it? And once I did construct that integral, that position, how would I find its derivative? So I want to investigate that question because it turns out to have a really useful answer. what I'd like to be able to do is take my velocity and some kind of initial position and I'd like to take those two pieces of information and find the position x of t based on that. Now, if I can find an antiderivative, good for me, great. But what if I can't? Because there are a lot of functions that we don't know antiderivatives. Am I right? For example, if I asked you, find the antiderivative of ln t, dt. Do you know a function whose derivative is ln t? No, right? So we seem stuck. Yeah.
Isn't it ln t?
Nope.
Is it x?
Yes, actually. Where'd you learn that?
It was a problem a while ago, so I looked it up.
Cool. All right.
Wait, what's that?
X ln x minus x.
Good. It works. If you take the derivative and check it, it works. All right, so we want to give x of t. So here's going to be my reason. What I'm going to do is I'm going to start at the initial position, and I'm going to integrate from 0 out to t. Take a look. And I'm going to integrate the velocity. When I integrate the velocity, I'm not going to be able to use the variable t because that's already taken. So I'm going to do a dummy variable, make up a variable, give me a variable. It's not t. X, that works. I'm going to integrate from 0 to t velocity, v of s ds. It could be v of w dw, v of x dx, whatever, just not t. Now what does this mean? Here's what this means. I'm going to take the graph of the velocity and I'm going to start at 0 and I'm going to go out to t, and here comes my velocity, and I'm going to find the total area, the net signed area under the curve. That net signed area represents the displacement of the object from 0 to t. And if I add the initial position to the change, I get the final position. That's it. So that x of 0 plus delta x gives me final x. This is every bit as a legitimate way of constructing the position as finding the antiderivative. And it's actually a little bit more powerful than antiderivatives because it allows me to construct a position when I can't find an antiderivative for a particular function. I'll give you a good example of this. Here's an example. Suppose that the velocity as a function of time t is going to be equal to t times cosine t. For t is between 0 and 10. And let's say that we find the position of the particle at time t equals 1 is equal to 8. That's a little high. Let's make it 4. And now we wonder, what is the position of the particle as a function of time t? And so using the idea of the definite integral, we can write the expression for x of t immediately. We can say that x of t is going to be equal to, so June, here's our label, x of t, is equal to the initial position plus the change from 1 out to t of, make up a variable for me, c, of c cosine c dc, just like that. And that variable could be any variable, just not t. It's a dummy variable. Does everybody see how I built that? Yeah.
That's a question. So, why do we start? So the initial
times t equals 1, right? Not t equals 0.
In this particular problem, what the reference value that I know is that x of 1 is
Okay,
equal to
so
12.
does that boundary was set to matter?
The domain doesn't affect our answer to the question.
Okay.
No. It's just going to carry down and give us a valid domain for x of t. Yes.
Are those supposed to be C's or T's?
C's, she wanted the variable c. If you don't like c, you can make it any other variable you want.
Can we make them K's?
You can make them k, you can make a w, that's common. X, s is actually really common. U is a common variable. Okay? Now, you ask, yeah, Peter.
Oh, so for the integral, why do we use cosine t? We have cosine t instead of t cosine.
Why do we not use t for the variable here?
Yay.
Yes, because t is the variable for my integral function. What I've done is to create an integral function. Let me explain how this goes. This is a graph of the velocity with respect to c. I'm going to start at t equals 1, and I don't know what c cosine c is going to look like. Let's see, it'll be 0 at 0, it'll be 0 at pi over 2, 0 at 3 pi over 2, and it's going to do something like this. It's going to be something like that. And so we're going to start here, and we're going to go out to a time t, and we're going to find all of the net signed area from 1 to t. That's our displacement. And then we'll add on the initial position to get our final position.
Okay, so, but why do we not have like t cosine t for like in that integral?
Because t is already taken as a variable. Yeah,
Can you scroll up just one?
sure. So what this integral function does is compute total change. If I add on to that the initial value, then I get the final value. That's it. It's a really simple concept. But this opens a big question. If I now take the derivative of x of t, what will I get? What does it mean to take the derivative of one of these integral functions? Any ideas? Based on your experience with motion, if I take the derivative of x of t, what should I get? I should get v of t. That's exactly right. And that suggests to us that when I take the derivative of one of these integral functions, I should get the integral. Ooh, let's see if that's really true. I'm going to do this very generally. What I'm going to do here is to compute the derivative of x0 plus the integral from a to t v of x dx. And that's going to give me, or let me make it v of w dw so we don't confuse that with position. And what that's going to give me is the rate at which the position is changing. And I suspect that the answer to this question ought to be v of t. Is everybody following what I'm doing here? Okay. Now, unfortunately, I don't have any derivative rules at all for integral functions, so I'm going to have to create one. In fact, tomorrow we're going to make it formal and call this derivative rule the fundamental theorem of calculus part 1. So since I don't have any derivative rules, what I'm going to have to do is to go all the way back to our limit definition. You remember that? The limit definition is the limit as h goes to 0. Let's see here. That's going to be, I have to evaluate the integral function at t plus h. And then I have to come back and evaluate it at t. seems yucky. And all of that divided by h. In case the notation is confusing to you, let's slow down and see what this really is. What this part in red really is just x of t plus h. And what this part in blue really is just x of t. So I am finding the displacement between x of t plus h and x of t. And I'm dividing that displacement by the amount of time that elapsed to get an average rate of change. And then I'm going to let h go to 0, and that'll give me an instantaneous rate of change. So this is actually a familiar concept to us. We've been calculating rates of change for a while. The only question is, how do I simplify? Well, I do notice one nice thing early on. What one nice thing do you see that will let me simplify a little bit? The x zeros go away, meaning that the derivative of a constant is 0. Oh yeah, I knew that. The next thing that I see is that I can write this like so. Minus the integral from a to t of b of w, dw, like that. Okay, well that helped a little bit, but it doesn't help a whole lot. So now I wonder, what can I do with this? I don't have any algebra, so let me go to the graph and see what we're talking about. What we're talking about on the graph of velocity is to start at A, and then we're going to go out to T. And this area right here in black represents the integral from A to T of B of W. It also represents the displacement of the particle starting at A going up to T. If I add a little bit, T plus H, I add a little H to my T, then the integral from A to T plus H represents the entire displacement from A all the way up to T plus H. And you can see that when I subtract the two, what happens to the black and the red? Does everybody follow me, or am I going too fast?
The only thing remaining is the red.
Is the embed. Sure, I'll explain it again. The quantity in red is the displacement from A to T plus H. And that's represented as the area from A to T plus H right here. Okay? And the quantity in blue, let me take this guy in blue and make him blue, is the area from A to T. That's the displacement from A to T. And so my question is, when I subtract the stuff in blue from the stuff in red, what's left? The difference between those two is this small little sliver right here, right? Okay? And so what that is, if you look at it, is going to be the limit as h goes to 0. This integral minus that one is just the integral from t to t plus h of the velocity. Think about that for just a minute. Yeah.
I got this right, but if you divide the area difference by h,
Yes.
don't you get like the mean value of that integral, or h equals 0?
Yes. Very, very, very good. Okay. Yes, that's exactly where we're going with this. Okay. Any other questions before I come to the main point? Because we're about to do something profound here. All right. Does everybody agree that the area that's just red right here, from here out to here, this area represents the integral from t to t plus h. Does that make sense? Yes. Okay. AG, good with it? Yes, no? Good?
Mm-hmm.
definition of the derivative, simplified, and now we appeal to the idea of areas to take all this and simplify it like that. Yep. Now here comes the profound point, and it's Peter's point. Very good, Peter. And that is, on Friday, what we did was to take and represent averages in terms of integrals, right? So if I were to find the average value of the velocity, that average value of the velocity on this interval, the average, would be written as 1 over t plus h minus t times the integral from t to t plus h of v of w dw. This is our average value, right? Which is the width, which is the area divided by the width. But if you look very closely, this average value expression that we have is exactly that expression right there. We didn't realize it, but what we found right here was the average value of the velocity on the interval t to t plus h. And that's going to be as h goes to 0. Yes.
Why didn't you take off the other part of the area?
That's a good question. I was subtracting two areas. And so what I said was, if I subtract these two areas, then what I have left behind is just the area that was not canceled. Does that help? Yep. Here's another way to look at it. If you look at it in terms of our additive interval property, if I integrate from a to t, and then from t to t plus h, what I get is the integral from a to t plus h. So that if I subtract off a to t, I'm left with just t to t plus h. So here we have the average velocity as h goes to 0 on the interval t to t plus h. Now, as h goes to 0, what happens to the width of my interval t to t plus h? It's going to squeeze down, and when it squeezes down to 0 width, I end up with only one possible value for my average, and that's v of t. So that what I have discovered through a fairly involved process that I will repeat tomorrow when we do fundamental theorem is that the derivative of the position as computed here is equal to the velocity here. And since two functions with the same derivative are the same function within a constant, it must be that my position as computed with the definite integral is the same function as the antiderivative. What we've discovered is a new way, and possibly a more powerful way, to compute antiderivatives. Okay. Now, let's see how we might graph these things so that we can get a good picture. For this particular position function right here, I can't find an antiderivative, so I'm going to need to appeal to my calculator to graph them. Everybody grab your calculators, and I'll show you how these graphs go. If I want to graph an integral function, and I'm going to set it up like this. I'm going to set y equal. I'm going to set y equal to 4 plus. That's my initial value. And now to do an integral, I'm going to do math function int. And when I do, it sets up a nice integral for me. Unfortunately, the only variable the calculator knows is x, so I'm going to have to use x for everything. Below. And I'm going to integrate from 1, the 1 was my starting time, right, in that particular problem, out to x, and my function, my velocity function, x cosine x dx. Now again, here I use x for both because I don't have a choice. But I do have a choice about getting the right number of parentheses, so I will do that. Okay. And then I'm going to set my window size 0 to 10, because that was the domain of the problem. And I don't know what to make my y values. Looks like that'll work. And so I graph it. And when I graph it, it is slow. And the reason that it's slow is that for every single point it calculates on the graph, it's doing a definite interval. It's adding up rectangles. 100,000. Yeah.
If you have the other type of calculator, would you do it function interval x comma 1 comma x cosine x dx?
It would look, yes. So while this is finishing its graph, I'll show you what it would look like. On the calculator, you'd say y1 is equal to 4 plus, there's the initial value, and then the syntax is function in up. You're going to have the function, x cosine x, the variable, which is always x, and the limits of integration, which in this case are from 1 out to x.
Wait, why do you have the x before 1?
This is dx.
Oh, right.
I saw the other function.
What's that?
I saw the function is just cosine x.
No, it was it was t cosine t. It was the original velocity.
More extra.
And that's why we had to use.
Wait, what was the... I got an argument for my graph.
You got an error.
It says,
Error.
I said this, and I can look at it so I can
Oh, you have a parentheses problem. You need to close your parentheses. I don't know one or use. Because of that, it's trying to get it just as plus an x1, x4, what?
Mine is going a little bit interesting and just going straight up. Like
I'm betting you're in degree mode on your calculator.
oh, wow. It's like
Yeah, same thing
as
as
physics test.
yeah, it should be right. Can I look at your window size? 0 to 5. My window size is 0 to 10. Yes, it does take forever. It takes a really long time to do that. And it takes a long time to do that because it is computing a definite interval for each one. So this method of computing antiderivatives, essentially, is powerful, but it's slow. Why is it powerful? Because I can now find the antiderivative of any function whatsoever. You tell me f prime of t equals blah blah blah, and I can immediately write the antiderivative as the integral from 0 to f of 0 plus the integral from 0 to x of f prime. See? I've got it. I've got an antiderivative for anything. But the cost is, when I go to actually compute it, I have to wait for the calculator to compute a definite integral for each point along the curve. And that's a really slow process. So nothing's for free. If I can find an antiderivative analytically, it'll be a lot faster, and I'll do that. But if I can't, this is a great backup tool, isn't it?
Yeah.
5 minutes, AP exam.
Yep. Tomorrow we'll look at a similar problem, but we'll look at people going into a park and coming out of a park. Okay? And we're going to find the maximum number of people that are in the park.
How are we going to do like this in cycle?
Tycoon roller coaster.